So there's our cis and trans butene that are not superimposable upon one another. All right, you can go back to this slide. We'll look at it real quickly here, but we're going to apply what this slide says to 3 or 4 or 5 different molecules. What does it say? All right, it says if one end of the carbon-carbon double bond has 2 the same groups on it, then you don't need cis or trans. If either one of those 2 carbons involved in the double bond have 2 things on it that are the same, then you don't need cis or trans in the name. That's what that first sentence is telling you. Both carbons of the carbon-carbon double bond must have 2 different groups attached. And then you need to find something that is the same on both of those carbons that make up the double bond. All right, I'm going to work us through some of this and then decide, are those 2 things that are the same on the same side of the double bond? Cis. Are they opposite sides, across from each other on the double bond? Trans. Okay, now this is kind of applying this. Here's a molecule. It has a double bond in it. So we're focused on these 2 carbons. Now we ask the question here, does this carbon have 2 different things on it? Yes. Okay. If it does, then go on to the second question. The 3 questions we're going to ask right now need to all have the answer yes. If they are all yeses, then it's cis or trans. If any one of them is a no, then it's not cis or trans. You don't need cis or trans in the name. So first question, does this have 2 different things on it? Yes. Okay, go on to the second question. Does this carbon have 2 different things on it?
Yes.
Yes. Go on to the third question. Do these 2 carbons have something on them that are the same? Yes. So that is a cis or trans. All right? A cis or trans what? These are the 2 things that are the same. Now that looks like a methyl group, but actually if we then come back to IUPAC, now you come back and name it by IUPAC. 1, 2, 3, 4, 5 carbons long. Where does the double bond begin? Carbon number 2. What did we leave out? A substituent. 1, 2, 3, how many? 1. That's the only thing we left out. 1, 2, 3, 4, 5. There's 5 carbons represented here. That looks like a methyl, but it's not a methyl substituent. It's the beginning of the longest chain. Okay? So the only thing we left out was right here. And so that is a methyl. And where is it? Carbon number 3. Okay, now we go back and look at these 2 things. Even though we didn't call that a methyl, that is the same as that. It's sitting out here on the end of the molecule, but it's the same as this thing. So these 2 things are on the same side of the double bond, so it is, Christian? Cis. All right? So that's cis, 3-methyl-2-pentene. So just naming it 3-methyl-2-pentene is inadequate. It's not really adequately defining that because there is also that. Okay, this is not superimposable upon that. These 2 methyls are across from each other. That would be the trans. So that thing does have an isomer. That would be its geometric isomer, trans 3-methyl-2-pentene. So there are two 3-methyl-2-pentenes. They're geometric isomers of one another. Yes? Trans. That would be trans. This one would be trans 3-methyl. I think so. 1, 2, 3, 4, 5. It's still 5 long. This methyl is still on the third carbon. So it's trans 3-methyl-2-pentene. Double bond still begins on the second carbon. Yeah, neither one of these two carbons have two of the same things on it. Here's another example here. They don't have to be methyls. They could be chloros. Different things can come in here. This is 1, 2, 3, 4. This is 1 butene. But this carbon has two different things on it, a hydrogen and a chlorine. This carbon has a chlorine and a CH2CH3 on it, two different things. And these two carbons each have a chlorine on it. So those chloro groups are trans to one another. So it's trans 1,2-dichloro-1-butene.
So in the previous example, Professor, how come we didn't put dimethyl methyl groups? We put cis-3-methyl. Wouldn't that be because we have one.
See this name? 1, 2, 3, 4, 5 carbons. So that carbon has already been accounted for in this name.
So we don't have to put it as a dimethyl.
It's not a dimethyl. It's only a 3-methyl pentene.
Because there's only one technically.
Okay, looks like it's a dimethyl, but it isn't.
So then why? Oh, never mind.
Okay? Okay? This takes some time to noodle. I don't mind you noodling it. Some of this you have to noodle outside of class. So keep noodling. All right? Because it will run you around in a corner. All right, so noodle this. Here are 3 molecules. Let's take one at a time. But let's do this as a class. One at a time. We're going to look at this one, then that one, and that one. We're going to ask these 3 questions, and we're going to decide whether this has a geometric isomer or does not. Yes or no? Does it have a geometric isomer? Does that have 2 different things on it?
Yes.
Does that have 2 different things on it?
Yes.
Do these 2 have something that's the same?
Yes.
Okay, so yes. It does have a geometric isomer. And the 2 things that are the same, are they on the same side of the double bond or opposite one another?
Opposite.
So it's going to be trans. Okay, you can come back later and name these if you want to, but that's not the purpose here. Right now it's to solidify, how do we tell whether it has a geometric isomer or not? You ready to go on to this one?
Yes.
Does this have 2 different things on it?
Yes.
Does that have 2 different things on it?
Yeah. No.
Yes, no, maybe?
No.
It's either yes or it's no.
It's a yes. It's the same. It's a yes.
Yes or no? It has things on it, but those things are identical. They're the same thing.
Yes.
That is the same as that. I mean, if you named that, you'd say, oh, that looks like an isopropyl group. So does that. They're the same. Because they are the same, they're superimposable on one another, and they're not going to generate 2 different isomers. So answer here, no, because we got a no answer right here. Does that have 2 different things on it? No. You get a no answer, then it doesn't have a geometric isomer.
That means you don't have a cis or a
So you do not put cis or trans in the name. It's not necessary.
Then what is cis?
You just name it, whatever it is. I mean, here's 1, 2, 3, 4, 5 carbons long, it looks like. 1, 2, 3, 4, 5. Oh, wait, 1, 2, 3, 4, 5. I can't get any more than 5. I can only get 5. So then it'll start getting ugly, because you're going to get 5, or let's see, 1, 2, 3, 4, 5, or 1, 2, 3, 4, 5. I see, I can 1, 2, 3, 4, 5. No matter what I do, I can only get 5. Oh, wait a minute. This is not good. 1, 2, 3, 4, 5. What did I do wrong there? I ignored that. So I have to start here. 1, 2, 3, 4, 5, 4, 5, 4, 5. Okay, so that's a pentene, and then you would name it from there. But it wouldn't have cis or trans in front of its name. This thing would have, this one over here would have trans. It's trans something or other. But neither cis nor trans. Okay, now let's do this one. Does that have 2 different things on it?
Yes.
Does that have 2 different things on it?
Yes.
Do these 2 each have something that's the same? Yes. Okay, yes. And those things that are the same, are they on the same or the opposite side? Same. Cis. Now let's go ahead and name this one. This one's pretty, that one got a little bit uglier, but let's just name that just to show you how simple this name is. What's the longest chain? 6. So it's called hexene. The double bond is where? 1, 2, 3, 4, 5, 6. 6 carbons long. You don't just kind of come over here and call that a substituent. You can keep going. I didn't pick up my finger. That's a continuous chain. And it starts out on the 3. And that's the full name. 3 cis-3-hexene. There's no substituents on there. That's it. And so to just contrast that, if I had this molecule, there would be trans. That's trans 3-hexene.
So whenever it's diagonal like that, it's going to be trans.
Yeah, we're coming here, and this thing is the same as that. We don't call it a substituent. It's been incorporated into the longest chain. But they are opposite each other. You come through the double bond, and you go out the other side to continue on with the chain. So that's trans 3-hexene. Okay? All right. Now let's make it a little bit more complicated. Let me. I'll draw this cis 3. Oh, we got cis. We just did this. So let's go on to this. I'll come back. That one there is your. That's for your party this weekend. Hey guys, let's draw this molecule. Would that go over by like a PB balloon? Okay, that's a chemical joke. PB is what? Lead. Lead balloons don't go over very well. All right, let's draw one of these. There's trans 3-heptene. Let's draw trans 3-heptene. Now, and then you can try one, and then I'll draw another one maybe. But here, we're going to do this one, trans 3-heptene. Start with the double bond. So I got a heptene, and a double bond is going to have this kind of configuration around it. I'd like you to think about that shape when you see a double bond. All right, so I'm starting right there. It's heptene, it's 3-heptene. So there's carbon number 3 right there. So here's carbon number 2, and there's carbon number 1. So I only have 4 carbons. How many do I need? 7. It's trans, so I'm going to continue my chain here. So I've got 1, 2, 3, 4, 5, 6, 7. All right, now I've got the skeleton. I've got the backbone of this thing, and I can just put my hydrogens. And that's it. I only have 1 hydrogen here and 1 hydrogen here. They are trans to one another. This is trans. This is trans, although this isn't identical to that. We come in one side of the double bond and we go out the other side of the double bond. We don't continue on the same side of the double bond. All right, so why don't you do cis 1-chloro-2-pentene. So draw this one. Cis 1-chloro-2-pentene. Build it off of that double bond. Yeah, that's the 3rd carbon.
Yeah, it's like this.
So you got a carbon in there you shouldn't have, right? That is that carbon, right? So 2-pentene. So 1, 2, 3.
Oh, right.
Okay, so get rid of that carbon.
Confused. The double bond is on 1.
1, 2, 3, 4, 5. No.
Then where's the double bond?
Well,
It's
2.
on, it's on 2? Okay. Okay.
That's what that number's for. Okay?
Okay.
It's on number 2, on carbon number 2. Okay, the double bond is on carbon number
Hold
2.
on.
What?
I did the wrong one.
Okay? Okay, it's really, really useful for you to try to do these because, you know, that's where the rubber meets the road. Oh, you got a double bond there? 1, 2, 3, 4, 5. And what is it? It's 1-chloro and it's trans. Yeah. No, it's cis. It's cis. I'm sorry, cis. Right. Good. Good. Yeah, see, these are cis to one another. And this also comes in, goes out. That's good. Okay. So cis 1-chloro-2-pentene. Put your double bond. The double bond starts on carbon number 2. So carbon number 1 is going to be right there, and there's going to be a chloro on it and a hydrogen. And then it's going to come out this same side of that double bond. And there'll be a hydrogen down here and a hydrogen down here. Okay, so you've got the double whammy here. You need to be able to look at a structure and figure out whether it is a cis or trans, has a cis or trans isomer. And you need to be able to take a name and draw the structure. Okay, and there's some others there to practice which you should try to do. And remember, I have office hours. There are tutors down in LOH 230. Do these things. You get into a test and you go, oh man, I'm going all blank. Well, you didn't try enough molecules. Don't go blank. This is like kinesiology. You know, you don't build the muscles unless you do the exercises, right? And you're building muscles in your head. They don't show as much
But they're there.
unless you're a geek, in which you show off those muscles,
Oh, yeah, no.
and or you're a chemistry professor. All right. Let's go on. Isoprenoids, we'll talk a little bit more about those in chapter 17. They do occur in nature. As a matter of fact, nature uses these things to make steroids. They start with these isoprenoids. That's 2-methyl-1,3-butadiene right there. That's what that is. That's the name of that molecule. It's an isoprenoid. Okay, we got enough minutes here. You just have a few minutes. Probably some of the most important reactions I'm going to show you are these 4 addition reactions to alkenes. We're only going to do one. And then you're going to build one little muscle in there. You're going to come back Monday and I'm going to tell you all 4 of them. All right? So that I don't want you to strain any muscles. You would if we did them all 4 at once. All right, so let's do 1. There's going to be 4. The names of these reactions are all going to start with an H. You're going to love that. The name of the reaction it's named after the reactant that the alkene is reacting with. So the first one is a very simple molecule, hydrogen. When we react hydrogen with an alkene, it adds across the double bond. That's why we call it an addition. That's the class of the reaction. So if I were to take something like ethene, has a double bond in it, and react it with hydrogen, I would be hydrogenating. It would be the hydrogenation of ethene, and I want to show you what that would produce. So up here, I'm going to just quickly just kind of give you an idea what ethene, remind you what it looks like, plus hydrogen. We'll complete this in just a second. But down here, I want a diagram. In a diagram, here's my ethene. I want to show you how this reaction proceeds. And here's my hydrogen. Hydrogen is diatomic. It's 2 atoms of hydrogen sharing 2 electrons. That's a covalent bond. We've got ethene. We've got a double bond here. There are 4 electrons being shared right here. So I'm going to show those electrons here for a second and show you what happens. Hydrogen comes along. There's a catalyst. You need a catalyst. It's usually platinum, palladium, or nickel. The compounds. It's like chlorplatinic acid is a hydrogenation catalyst. Palladium dichloride, nickel chloride are hydrogenation catalysts. You only need a little bit of them, fortunately, because platinum is very expensive, more expensive than gold. Platinum is. But it's used as a hydrogenation catalyst. Now here's what happens when this catalyst gets these 2 near each other. This electron and that electron move up into there and form a bond, a new bond. And this electron and that electron dump down into here and form a new bond. So this bond is gone. Those electrons are gone. Those electrons have come in here to form a new covalent bond. These electrons are gone. That double bond is gone. And so what you get, let me just finish this, and then you can noodle it. You can leave and noodle it. Is this making you hungry? Okay, I'm going to quit this rhetoric, all right? I'm going to get back to technical language. That's what we get. What do we get? What is that? What molecule is that? Ethane. We've gone from ethene to ethane. The only thing ethene lacked to be ethane was 2 hydrogens, and by hydrogenation, they've been added to it. So what we get here is ethane, and that's it. That's the final product. 6 hydrogens, okay? There's 3 more of these. There's halogenation, hydrohalogenation, and hydration. If you want to study those 4 H's, hydrogenation, halogenation, hydrohalogenation, and hydration. We'll do the other 3 on Monday. And the Chapter 11 homework's due on Wednesday. Be ready for Chapter 12, because we'll spend about 20 minutes finishing up Chapter 11, hopefully, and then dive into Chapter 12.